Good morning, I'm Hugh Dyer, Director in RSK's Geosciences business. Welcome to the April edition of our 2025 series of Down to Earth webinars. These will cover a broad range of subjects and are available afterwards on our YouTube channel alongside our previous talks. Our talk today will be given by Yusuf from our Safe Ground team within the Geosciences business. Yusuf will give an overview of the importance of good utility detection surveys when breaking ground. But firstly, a note on our housekeeping during the talk. All attendees' microphones are automatically muted throughout the webinar. During the presentation, you can post questions online and there'll be a Q&A session at the end of the presentation. We'll answer as many of the questions as possible at the end of the talk. Those that can't be answered due to time constraints will be answered after the webinar. Shortly after the webinar, you'll receive a link to a short survey. If you can take a few minutes to provide feedback, please, so we can improve on future webinars. Now, please let me introduce our speaker today. Yusuf has extensive experience of PAS 128 surveying from his nearly 6 years of working within the RSK Safe Ground team, working on a range of sites from small complex utility heavy sites to tracking major energy infrastructure across large sites. He has gained QCF level 5 for utility mapping and surveying and has a great understanding of the complexities for utility tracing, mapping and interpretation of geophysical survey results to get the most out of the information gained on site. So I'll hand over now to Yusuf to guide us through the complexities of utility and service tracing.
Lovely. So thank you, Hugh, and good afternoon, everyone. Thank you for joining us today for this webinar. Let's get started. So the aims today are to discuss PAS 128 and more specifically what that requires and how, for example, it's implementable before, during and after site investigation. I will also talk about how PAS 128 links into both HSG47 and G5.15 and the importance of that safety aspect in our work. And then finally, I'll discuss how this is relevant for buried service avoidance and more specifically service avoidance surveying that we would do, for example, prior to breaking ground for site investigation. Okay. Early doors, let's ask ourselves this question. What would the first thing a client want to know when having a utility survey commissioned? Most likely, would it be to do with the cost, the time it would take? There's a few different answers to this, really, depending on the needs of the survey, but a likely answer to this question would include what services are we expecting on site and where are we expecting those services to be? So bearing this in mind, let's have a look at how that comes into practice in the UK. So I'm going to show you some statistics that summarise the current landscape. This is as per Line Search Before Your Digs, Digging Up Britain report for 2024, which is this document here. This basically shows how many requests for service records Line Search have obtained throughout 2023. So there were just under 4 million Line Search requests that year, which is the largest on record. That equates to an increase of 160,000 from the previous year, a 52% increase from 5 years prior, and actually that number has tripled from 2013, so over a 10-year period. So some positive trends there, showing that the understanding of the importance of obtaining that statutory information is becoming more embedded across industries, which of course is a good thing. But, and there is a but for this, risks do still exist. As you can see from this graph from the Utility Strike Avoidance Group in 2020, despite there being a generally higher trend of line search inquiries on the right-hand axis, we still can see reported service strikes are consistently above 100 a month on the left-hand axis, and that actually rises above 200 in August and September. So this would suggest that there is a danger of relying on service records alone, especially because line search results will show public records, but they don't always show private records. And even when those private records are accounted for, the position of services can differ substantially from where they're plotted on record drawings. So what can we do about this? Well, this is exactly where PAS 128 comes in. So PAS 128 was first created in 2014, which is this document here. The image on the right shows the most up-to-date version from 2022. The front cover of the 2022 version is actually a photo of a survey that RSK were undertaking. RSK were involved in the steering group for the 2014 document and were actually the authors of the 2022 update. So that shows how we feel about the subject. PAS 128 ultimately was brought in to help clients obtain a utility survey whilst also being protected from poor results and their consequences, such as a service strike. The aim of PAS 128 is to provide that consistency, really, across industries for data capture, which would create a blueprint of sorts for deliverables and then an accountability for the results of surveys that are undertaken. It's also provided a more clear definition for survey types and accuracy levels of results that clients should expect from the surveys that they want to be undertaken. So PAS 128 splits up these survey types into 4 categories. These rise in quality and accuracy from D, which is a desktop record search, which is like what I've described earlier with line search, through to C, which is a site reconnaissance or a site walkover, through to B, a detection survey, all the way through to A, which would be a verification survey where the service has been exposed and then its position is recorded to a high accuracy. So as we move forward, we're going to focus on survey type B and ultimately how types D and C can help along the way for that. So let's consider the road to B. How can we produce a higher level of quality and accuracy for a type B detection survey in PAS 128? Well, it is a requirement for a type B survey to have a desk-based search of utility records, and as part of the detection survey, a site walkover must be undertaken either initially or prior to the type B survey taking place. So by definition, if a type B survey is commissioned, then both type D and C surveys will also be a part of that type B survey. In practice, that site walkover with knowledge of the service records is really helpful to establish not just the amount of inspection covers on site, but any valves, services above or entering the ground, general ground conditions, access across site, and even what type and method of B survey is actually best suited to the task. Let's explore what options we have on the table for that. Well, first things first, you need a site team, such as this gentleman here. As you can see, undertaking a PAS compliant type B survey can put a smile on anybody's face. But in all seriousness, a type B survey has the most complicated aspects of PAS 128, as it is the most complicated part of utility mapping in general, which makes sense. So for this, PAS 128 states that 2 techniques as a minimum are to be deployed to detect and identify services. That's most commonly GPR and electromagnetic location, or EML for short. A quality level must be identified and acknowledged ultimately by the person or persons undertaking the survey at each segment a utility has been detected. And then these quality levels range from B1 to B4 as per this table here. Also, if post-processing of GPR data has taken place to achieve a more thorough and complete interpretation, each of these quality levels is suffixed with the letter P as per the table as well. So expanding on this further, the highest level of accuracy for a type B survey is a B1 or a B1P, depending on the presence of post-processing. And until 2022, you could only attribute a B1 quality level if the utility had been detected by 2 or more geophysical techniques. However, one of the revisions for the most up-to-date version of PAS 128 is that a B1 can now be achieved with 1 technique only. So this is the fun bit. One technique can obtain a B1 quality level as long as what is known as field symmetry is achieved using EML, and this happens when the peak and null measurements are either equal to one another or are within B1 tolerances. It's important to note that B1 is ultimately less likely to be achieved when multiple electrical and metallic surfaces are in close proximity to each other. So for example, in like a pavement in London city centre, you can imagine there's many a surface in that. The other way to obtain a B1 with one technique is if GPR obtained depth and horizontal positions are established to the required accuracy level. Sounds really simple, doesn't it? Right? Well, clear evidence has to be made available to the client to justify a B1 quality level if only one technique is used. So that accountability that we've discussed in PAS 1 to 8 is there ultimately. The diagram on screen shows the accuracies involved in achieving those different quality levels from B1 to B3 as per the key, and ultimately how they differ from one another. Note that B4 is associated to records only, and therefore it doesn't have a horizontal or a vertical accuracy, which is why it's not described in this diagram or on the key. Cool, so now that we've discussed quality levels within a B survey, let's move forward into the different methods within that type B survey. There are 5 detection methods within the type B survey scope. All of these are related to the use of GPR, such as the one on screen. In most cases, this is related to the spacing between lines for orthogonal grids when collecting GPR data, but we'll discuss when that's not the case as well. So the scale moves from M1 through to M2, M3, and then into 3 types of M4, these being A, B, and C. Each of these methods can have post-processing as well, as highlighted here. Essentially, the higher the method number, the smaller the spacing between lines within a GPR grid. So as the table shows, M1 has a spacing of up to 5 meters, M2 up to 2 meters, M3 up to 1 meter, and then M4A up to half a meter spacing. There are some alternatives within these methods. So we have M1, which can also incorporate a perimeter survey. We have M4PB, which describes the use of a multi-antenna array, such as a dual frequency GPR system, being used orthogonally, or alternatively, you can use a stream seed GPR, collecting in one direction, which would then be combined with a classic single channel system, which would be collecting data orthogonally at half a meter spacing specifically. And then there's also M4PC, which is the use of a dual polarized multi-channel array, which is slightly different to the multi-channel array from M4PB, as using this system removes the need to collect in 2 directions. Although the survey team can collect additional cross lines within this if the resolution of services is not deemed suitable enough. So quite a few options within this framework of methods in the end. The final column on this table is important to consider as well when judging what's required for a survey of suitable detail. So for example, road surveys, particularly over longer distances, are a pretty good scenario for the use of an M4PC dual polarized multi-channel array, because that allows for an in-depth but also considerably quicker collection time. Much more ideal for larger surveys like that. An M4PA or B may be more suitable for a survey looking for structural evidence such as reinforced concrete or the base of slabs, in addition to buried surfaces, for example. And then an M1 or an M1P would be much more suitable for a greenfield area that either has no services or a very small amount of services expected to be within it. To show you then, M4PB or C would use something like this, which is a towed array GPR, whereas typically anything from M1 to M3 method surveys would use a standard cart like this one. So this brings us to an important question. If we have the choice of having our surveys as P with post-processing of GPR data, or not P with on-site markup of GPR targets, then why should we go down the P route? Simply put, speaking from experience, Ps are a good thing. GPR data is complicated, and whilst you have that real-time data when collecting it on site, which is great for having immediate information and on-site marking up of features, that's all good. In that scenario, undertaking a detailed interpretation of the data isn't really possible, especially in busy urban areas, brownfield sites, where those data responses you're getting on the GPR are quite complex, such as the examples you can see on screen. There's quite a lot going on in those examples. So really they would require that post-processing aspect to properly capture what we're seeing to that highest level of quality we can obtain. It always comes back to that really with PAS128 surveys. We want that quality and also that accountability within the work that we do. So let's see how a PAS128 survey can look with a real example. This is also going to go into how accountability within PAS128 is actually put into practice within a suitable working structure in the coming slides. So for this example, the survey was commissioned for an RAF base. The site was over 40 hectares, so a pretty substantial survey area in the end. The client was looking for buried utilities, but also any buried obstructions to be presented in both 2D and 3D. As the survey area included runways, grassed areas, buildings, all sorts of things, it was proposed by RSK to use methods M4PC to M1P as appropriate for the site. And as per PAS128 standards, this included GPR and EML detection in tandem with one another, as some of the services on site couldn't be detected with EML alone. So, for example, any of the plastic potable water pipes would not be detected with the Cat and Jenny. So we needed that tandem work with the GPR as well. So went on site. This turd array was used on runways and some grassed areas where ground conditions allowed for us to, alongside a cart system where the turd system was not suitable. As per PAS128, orthogonal grids were collected with the cart, with the maximum coverage obtained as possible when using the turd system. And then at the same time, we had survey teams that were undertaking the EML surveying through lifting and detailing inspection covers, and by tracing utilities as appropriate through both direct connection by clipping or clamping onto services, or passively using the Cat and Jenny in tandem. So you can imagine, for a site that was over 40 hectares in size, the survey took 3 months to complete, with a lot of members of staff involved from different RSK offices and a huge amount of data collected over that period of time. So it was important to have an organised structure for the site works as they were happening, but also to be PAS128 compliant when producing our results. So let's see what PAS128 details for this from a results perspective. So straight out of the PAS128 document, PAS128 requires transparency of the work done and the retention of survey data and records. It's a requirement for all data to be recorded and retained, even if there isn't a post-processing element involved. So what does that look like in practice? So during our case study example, we produced a clear folder breakdown to distinguish the stages of the post-processing cycle. This was the case for site notes that were then split into relevant subfolders for EML and GPR notes. An example of the tracing notes being this IC schedule on screen. And we did this for the collected data as well. Having data trackers and separate folders for raw data through the processing stage to dropping into the results drawing allows for each step to be accounted for and fully auditable at a later date if necessary, as per PAS128. Having the structure in place ultimately increases the likelihood of eliminating error to produce a higher quality final product, which is what everybody wants at the end of the day. So in the end, traces that were topographically surveyed on site and GPR post-processing combined to produce a comprehensive result. And if we take this area as an example, then we can see that some B1Ps were achieved along the way, which is ideal. With the survey, we had to be confident that we can stand by the accuracy of our results, such as the ones on screen. And with all data and processing steps available for review and audit, as we've seen on the previous slides, it means that if the client chose to, they can request the data for themselves, or actually even for an independent person or team to review it if they see fit, which is good. So we can see that there were benefits to following the PAS 128 standards. The client in the case study, and ultimately clients in general, are protected because the practitioner, or practitioners in this case study, must specify and stand by the accuracy of the results that they've achieved. So say something was missed or is inaccurate, if that practitioner says something along the lines of, well, the radar wasn't suitable for this area, and just leaves it there, well, there has to actually be evidence and clear reasoning behind that statement, so there's not really any hiding place. Something else to consider is a pretty crucial balance of cost to undertake the work and the time taken to complete a comprehensive survey and to ultimately produce a high quality, high accuracy result. This was happily achieved on the case study, and that led to the client returning to us for more site works a year later on the same site, which is great, shows that things went well. Okay, so we've discussed PAS 128 in some detail from a technical perspective. So how does it tie into HSG47 and G5.15 in terms of the health and safety aspects? So starting with HSG47, this is the HSE document which provides a best practice to avoid danger from buried services when breaking ground. The safe system of work from HSG47 has to be employed. And you can actually see here that those quality levels that we've discussed earlier from PAS 128 fit into the different stages of that system. This is actually something that RSK have also employed into our own guidance, G5.15 as well. So G5.15 is RSK's system that any RSK Group company has to follow if they want to obtain a permit to dig and break ground in anywhere. It's a pretty robust system that satisfies HSG47, implements PAS 128, and allows for work to be commercially viable, whilst also accounting for the realities of site work that I'm sure we all know. We can see in the system familiar PAS 128 elements again, such as having up-to-date service record drawings, site walkover with that full set of record drawings, a utility detection survey undertaken with 2 geophysical techniques with cover lifting and the identification of services included within that, and that all data is recorded and retained. An important point to note is that if there are any deviations from one of the best practice components within G5.15, so on the right hand side, those blue coloured boxes, this actually triggers an approval process that needs to be discussed, approved, recorded, and ultimately signed off by a competent director. There's also a decision matrix which aids this discussion and decision making process. So if GPR and EML service avoidance is not going to be employed, there would need to be a genuine practical constraint that stops them being deployed, or alternatively that the risk of services is very low based on the work and the environment that we're going to be working in. An example of that could be when undertaking soil sampling from a stockpile of earth with hand digging techniques, for example. Following that G5.15 guidance, the immediate information that's required for service avoidance for the purposes of site investigation is available. So we produce a form on our field tablets, which reduces the need for paper, where any information required, photo evidence and a sketch is produced that accurately represents what was detected and shown on the surface. This is then presented and emailed directly to the lead SI engineer on site, which forms a part of the permit to dig system. So implementing and refining the guidance in G5.15 has directly helped to proportionally decrease the number of service strikes that we've had in RSK, which obviously is a trend that we want to continue, and ultimately shows that when these aspects of PAS 128 HSG47 and G5.15 are put into practice correctly, it makes a positive difference in increasing the quality and ultimately decreasing the risk of service strikes, which is ideal. So to summarise, PAS 128 has had a good take-up. It promotes best practice and measurable improvements in utility detection work. And I'll emphasise this point again, it requires practitioners to stand by their results with clear evidence and reasoning, which allows clients to have that protection in case of poor performance during the survey. It also helps to provide the client with that confidence in both the quality and accuracy of the surveys that are being done, and also requires that records and data are to be kept so that there is an auditable trail if needs be. And on that note, that brings us to the end of this presentation. So thank you everybody for listening, and are there any questions?
Thank you, Yusuf, for that presentation. You can pop your camera back on it. We've got a few questions that are coming in now, if you're okay to take these. So I think I'll start with this one. How would a client know what methodology should be requested, for example, for a brownfield site?
So it's a combination of ultimately knowing the size of the survey area, the amount of time that will be needed for that survey area to be surveyed, how dense services are expected to be. So is it somewhere, for example, that's been decommissioned, so we're not expecting a larger amount of services present anymore, or is it as it was where we have all the various different types of services coming into that area? It's also dependent on if there's any specific requirements from the end client as to a certain accuracy that they want. So for example, on petrol forecourts, we've previously undertaken M4P B surveys at 0.5 metre spacing, and then sometimes we've done it at M3P with 1 metre spacing. It depends on the preferred requirements of what we're trying to look for, because ultimately we're looking for those services, but sometimes we also want to look for buried obstructions as well. Again, petrol forecourt would be a good example of that. We might have buried tanks, or even where tanks have been removed and we have that backfill. We want to know where that is, potentially for contamination reasons. So ultimately, having that kind of thought process behind what is required for the site will help to determine that.
So it might be something for them to discuss with you and your team.
Yes,
to work
exactly.
out the best way forward.
Yeah, 100%.
Okay, excellent. How would the client ensure that the survey results that they've received comply with the PAS 128 standard that they'd requested?
So that would be kind of twofold. So we produce our results drawing with all of those quality levels on there at any given point that we've recorded a position of a trace. We also have a report that goes alongside that detailing what we've seen with the explanations of how we obtain those different quality levels. But I'll give the example of, I think I mentioned it in the presentation about a B1 or a B1P. So if we've detected something with two methods, so if we've traced, say, for example, a power cable at a certain depth, and we've also found a GPR linear feature at the same depth, then in the same position, then we can say, okay, these two different techniques have seen this. So in the same place, same depth, we're pretty confident that this is the service in its true form. But if, say, for example, we were tracing that power cable with just EML, there are 5 different steps that you can actually do on site when tracing that out to look for that accuracy. So I've mentioned peak and null. There's also the height difference test, so literally looking at the depth that you're seeing on the cable avoidance tool when on the ground, looking at that value and then seeing when you lift that cat above the ground by a certain distance, if that change in distance is corresponding. So say, for example, if I then put it on top of my boot which is 10 centimeters above ground. Does the depth change by 10 centimeters? If it does, then we're looking at a potentially greater level of accuracy. If it doesn't, then potentially the electromagnetic field's been distorted in any given direction, so we can't have that confidence in the same way that we're happy that this is a more accurate position. But yeah, as I say, we have to detail as and when what we've done. And again, because we have all of our data available for audit, if, say, for example, the client wanted to have a look at the GPR data and see, okay, where is this position for this particular service been picked? How has it been detailed? What depth? How has it been reviewed by somebody? That can all be given to them with examples.
Okay, now that's a good answer to that. In terms of, you said about doing fuel forecourts and so on, where there's a great concentration of utilities in there. How can you, from the different techniques, identify how many services are there and differentiate between them?
Yeah, so it's a combination of every aspect of a past survey, to be honest. So obviously we have the service records so that we have an understanding of what we would be expecting. We don't rely on that alone because obviously, as I mentioned, sometimes we have private records that are not going to be shown. Having that site walkover to establish how many covers we've got, if there's anything above ground, any trenches or scars, can help us to have a bit more of an understanding of what to expect. And then when we actually do the survey, lifting up the covers, detailing what's within them, tracing things out either directly or passively, clipping onto street lighting, all different things can help build that picture. And then when we've collected the GPR, put it through that post-processing step, we identify where we have linear features, possible linear features, obstructions, reinforced concrete. They're all different signatures within GPR data. So then when we transpose all of this onto our final drawing, we can have a direct comparison. Say, for example, if we've been told by the client that we're expecting certain services to be there, and we've got the records to show that that was the case, we've got the walkover that's established we're expecting a certain amount, then we can see where we've traced things and where our GPR targets are lining up to see if we've established where those things are or not and how they correspond to the records. But obviously there are occasions where we either see more potential features than we're expecting, or sometimes we also have a situation, for example, if we have a very deep sewer, privately owned, we didn't know before getting to site and lifting the cover for it that that's what was actually going to be present. Because it's, for example, I mean, I've had it before where I've come across 20-meter deep drainage runs in London, for example, and that's well out of the scope of what a GPR and EML, or specifically the Cat and Jenny, can detect. So obviously we've acknowledged it's there, but we then can't establish further just with those two techniques what happens after that. But at the end of the day, we produce as much as we can do from those two techniques and from all the other information that we have for the site.
Okay, no, that's excellent. And kind of leads on to my next question, which was about post-processing. So you mentioned the post-processing.
Yeah.
So is this always essential, or is this something that can really help out in particular uses where it's more useful?
Yeah, I mean, personally, I would say that having post-processing is beneficial. Just because, I mean, I mentioned it on one of the slides, the fact that some areas that we collect data are very dense in terms of expected services, but also buried obstructions, changes in surface, and we can sometimes struggle to distinguish things to the level that we need to if we just mark it up on site. If we have that post-processing step and go through all of the kind of like the filtering, all of the different aspects that we get that data so that it's ready to be picked in the clearest way, and then we then ultimately have kind of like our review from another person to make sure that it's seen in the correct way. So I could pick data in a certain way, my colleague could pick it in a different way, and then another colleague could do it in a different way again. So we want to have kind of like that verification from a second pair of eyes that we've spotted everything that we should and have that confidence in that, and then can bring it through to accurately transpose that onto our survey area, because we topo in our grids that we've marked up on site. So we can literally put exactly where we've picked a service there and then in the spot that it is actually showing on site. It just gives that extra confidence, I would say. Obviously for service avoidance surveys, we have the on-site markup, and that is fine for that. That's absolutely okay. But especially for more complex sites, larger survey areas, having that post-processing just allows us to have a bit more accuracy and arguably confidence that we've seen everything we should in the data. So I would definitely advocate for it.
Yeah, that's brilliant. That's great. Right, I think we'll end the questions there. So again, a big thank you to Yusuf for the presentation and for answering those questions. There are further questions, so once Yusuf has managed to recover from this, he'll have a chance to answer those questions and come back to you. Our next Down to Earth talk will be on Tuesday, 13th of May, and we'll be looking at the conceptual site model and the importance of identifying uncertainties in our conceptual site model. So please remember to complete the feedback following the presentation, and thank you very much for attending today, and we'll see you again in May.